Okay, so in this video we're going to be talking about blood pressure and how blood pressure is controlled in the body because, as I'm sure most everybody's aware by now, having blood pressure too high causes significant problems. Having blood pressure too low also causes equally significant problems. So let's think about blood pressure and blood. So because liquids can't be compressed, when you push on a liquid, pressure is generated. And if there's, if within the system there's pressure differential, if one area of the system has a high pressure and the other area has a low pressure, then the liquid will move from an area of high pressure to an area of low pressure. So much like we talked about from high to low concentrations in osmosis or in diffusion, with blood pressure, we also move materials from regions of high blood pressure to regions of low blood pressure. So in the systemic circuit, this moves blood from the left ventricle, where we have the highest blood pressure of about 120 millimeters mercury, toward the capillary networks, where we have a moderate blood pressure, 35 on the arterial side, and something like 16 on the venous side. And then eventually we bring the blood back to the right atrium, where we see probably the lowest, pressure on the low end there is about 2 millimeters of mercury. So we're constantly moving blood from where it's high blood pressure to where it's the lowest blood pressure. It's easy to think that blood pressure is going to be lowest at the capillary networks, but if that were the case, then how would we get blood back to the heart? Because we got to keep it moving from a region of high blood pressure to a region of lower blood pressure. So, when we want to track or monitor blood pressure in the arterial system, and that's where we do most of the monitoring of blood pressure, then it's most frequently measured at the brachial artery in the upper arm. So brachial artery is used, and when you're looking for what is a normal or an average blood pressure, well, we're looking for a peak pressure during ventricular systole of about 120 millimeters of mercury, while a minimum pressure, diastolic pressure, should be somewhere in the area of 70 to 80 millimeters of mercury. And we can also track pulse. Pulse is that expansion of a blood vessel and then the recoil as it returns to its more dilated size. And we most commonly measure pulse at the radial artery in the wrist. So pulse is measured at the radial artery, blood pressure generally measured at the brachial artery. Although sometimes you can use, say, the femoral artery to measure blood pressure. Sometimes even pulse is measured down near the ankle. So lots of different places that this information can be collected from on the body. So if you look in the book, there's a great illustration showing what happens to blood pressure as blood moves through the arterial system and then into the venous system. So let's see, we are looking here for, where's that image? Oh, here it is. It's in a blue box on page 585. So at the aorta, we can see that there is a fairly broad range of blood pressure, running between 80 and 120. And then as we get closer and closer to the capillaries, there's much less oscillation from a high to a low blood pressure until finally we make it to the capillaries where all of that oscillation is lost. So very little oscillation in blood pressure by the time we get to the capillaries. And on the arterial side, there's a nearly uniform 35 millimeters mercury blood pressure. On the venous side, as we've already talked about, blood pressure has dropped to about 16 millimeters of mercury. And so when we talk about the term hypertension, that is a condition of persistently elevated arterial pressure. So we're looking for repeated measures that show high blood pressure before that diagnosis of hypertension is made. And high blood pressure has many negative consequences on the heart, on vessel function, and on a lot of the organs out there in the peripheral tissues. So maintaining appropriate blood pressure is is a pretty important thing. So what are the factors that can influence blood pressure? And there's 3 of them. There are many factors that influence blood pressure, but cardiac output here is one of the biggies. So blood pressure is, probably the biggest factor that determines what blood pressure is this term cardiac output. And cardiac output is a measure of the amount of blood that's pumped from the ventricles into the arterial system every minute. And there are 2 factors that influence cardiac output. One is stroke volume. That's the amount of blood that is pumped from the ventricles with each contraction of the heart. So stroke volume tells you how much blood is pumped out. And then heart rate is the number of times that the ventricles contract every minute. And so to determine cardiac output, we multiply stroke volume by heart rate. And here's the good news: I'm not going to ask you to tell me what cardiac output. I'm not going to have you do the math, but I want you to be aware of what factors we can change to influence blood pressure. So if we want to increase blood pressure, we can do one of 2 things. We can either make the heart beat more forcefully, pushing out more blood with each heartbeat, or we can speed up heart rate. And we can also do both. So usually those 2 things aren't isolated in the system. Excuse me. So in an average male at rest, the cardiac output is something on the order of about 5 liters every minute. So if you increase stroke volume or heart rate, then you're going to increase the amount of blood being pushed out, which will also increase blood pressure. If stroke volume or heart rate decreases, then we would expect to see a similar decrease in blood pressure. All right, so cardiac output is a very important factor in determining what blood pressure will be. So is blood volume. So, this should say blood volume. There. So the average total blood volume for adults is about 5 liters, which is interesting that's also the, by minute, approximately the cardiac output. But there's no big relationship between those 2 terms, or those 2 numbers. So blood volume has a direct influence on blood pressure. If there's a decrease in blood volume, either because of, say, a hemorrhage, we've lost a lot of blood, or if the body becomes very dehydrated, then blood volume will certainly be affected by that. Then we would expect to see a decrease in blood pressure. Less blood volume makes sense that you would also have less blood pressure, or I hope it does. And so one way to restore blood pressure in a patient is to increase blood volume. And we can do that by pushing IV fluids rapidly into the venous system. That will restore blood volume, which will then in turn restore blood pressure. Okay, so cardiac output, the volume of blood. Here's a new factor. It's called peripheral resistance. And that's the forces that oppose the movement of blood through the blood vessels. So in order for blood to flow forward, it's got to flow with sufficient force that the pressure, or with sufficient pressure that we overcome the forces that are trying to slow the blood down out there in the peripheral tissues. And peripheral resistance is caused by friction between the blood flowing through a blood vessel and the walls of the blood vessel. So the only place where we're going to see a lot of peripheral resistance is anywhere that the blood is right up against the wall of the blood vessel. So smaller blood vessels, just as a function of of size to volume to surface area relationships, smaller blood vessels are going to have a greater proportion of their blood coming into contact with the vessel walls. And so that means that when, as the blood vessels become smaller and smaller, we're going to see an increase in peripheral resistance. So when blood is slowed down because of the friction, then that means that all the blood behind it is like stacking up, trying to get through whatever blockage this is. And, so vasoconstriction, making a blood vessel smaller, will increase the friction between the blood and the wall of the blood vessel. This will slow down the flow of blood and will cause higher blood pressure. It's sort of like, if you have traffic going into downtown and very little traffic allowed to leave downtown, well, then all that backup of the traffic creates a big old traffic jam. Same thing's happening with the blood. It creates a traffic jam for the blood, which is going to increase the pressure behind that traffic jam region. Vasodilation, on the other hand, will enlarge the size of the blood vessel, allows blood flow to go faster, and produces a reduction in blood pressure in the system. So vasoconstriction will increase blood pressure by increasing peripheral resistance. Vasodilation will decrease blood pressure by decreasing peripheral resistance. Okay, so we've got one more factor that can influence blood pressure, and that is blood viscosity. Viscosity, this term viscosity, is about the ease with which the molecules of a fluid can flow past each other. So this is kind of it's a chemistry idea. And so fluids with high viscosity, the molecules of the fluid don't move past each other very easily. So molasses, for instance, has a very high viscosity. Water, on the other hand, has a low viscosity. So if we increase the proteins in the blood or the number of red blood cells in the blood, then viscosity is going to increase. And so imagine now if we have been pushing water through a blood vessel, that doesn't require much pressure behind it. But if we replace the water in the blood vessel with a bunch of blackstrap molasses, then it would take a lot more pressure to push that blood through the blood vessel. So increasing viscosity is going to cause an increase in blood pressure, whereas decreasing viscosity is going to decrease blood pressure. So there you have it. 4 factors that influence the pressure of the blood in the arteries. The cardiac output, blood volume, peripheral resistance, and blood viscosity. So how do we control blood pressure? Well, the first thing is the way that we explain the control here is through the Frank-Starling law of the heart. And by the way, this is not a guy's name. there is no man named Frank Starling. Well, there may be a man named Frank Starling, but he's not got anything to do with blood pressure. There are two researchers. One guy had the last name Frank, the other had the last name Starling. And the Frank Starling law of the heart is pretty basic. It explains how we balance the blood flow into and out of the heart. So if we push more blood into the ventricles, the muscle fibers of the ventricles have to stretch within, of course, reason. And these stretched fibers then, when they do get to finally contract, will produce a stronger contraction. And as a result of the stronger contraction, we'll see an increase in stroke volume, which increases cardiac output, and therefore then an increase in blood pressure. If less blood enters the ventricles then, though, the fibers are not going to be stretched as much, and so they're going to produce a weaker contraction. That's going to decrease stroke volume, and which, when you then multiply by the number of lectures lectures, what am I saying? Let me try that again. So, if less blood enters into the ventricles, then that's not going to stretch the fibers as much, and so we get a weaker contraction, decreases stroke volume and cardiac output, and as a result, we're going to see less blood pressure in the system. So the point of the Frank Starling law of the heart is that the flow of blood into the ventricles is balanced with an equal flow of blood out of the ventricles. That's the goal that we're looking for. And that keeps the blood moving forward, and it helps to prevent increases in blood pressure because of not enough blood being moved out of the heart. There's also neural control of blood pressure, and it is managed by baroreceptors. We've talked a little bit about baroreceptors already. These are neurons or sensory receptors that are associated with neurons that are found in the walls of the aorta, the carotid artery, and they are sensitive to blood pressure. So if we see blood pressure rise, then that means we need to get the blood moving because the pressure is rising, because there's like a slowdown somewhere in the system. And so increase in blood pressure is going to initiate the cardioinhibitor reflex. That's going to slow the heart rate because it acts at the SA node, slowing the heart rate, and it's going to result in a decrease in blood pressure. So when blood pressure goes up, baroreceptors notice it, they send out cardioinhibitor stimulation, and blood pressure will decrease as a result. If there's a decrease in blood pressure in the system, then that's going to trigger or initiate the cardioaccelerator reflex. It's also from the medulla, just like the cardioinhibitor reflex that we've already talked about. And this cardioaccelerator reflex is going to speed up heart rate, and as a result, if we're pushing more blood through the system, then we're going to see an increase in blood pressure in response to that. Okay, so we can control it with these reflexes that are based on the information that comes in through a baroreceptor. We can also adjust blood pressure by controlling peripheral resistance. So also in the medulla, there are control centers that can either send out signals for vasoconstriction or vasodilation in response to blood pressure changes. So if we see a rapid, sudden increase in blood pressure, then we'll also see vasodilation, and as the blood vessels get larger, then there's less friction, and so peripheral resistance will decrease, causing a decrease in blood pressure. If, on the other hand, blood pressure suddenly decreases, then vasoconstriction will cause more peripheral resistance, and that will then increase blood pressure. So we can moderate the effects of either a sudden drop or a sudden increase in blood pressure by altering how much, especially the veins, are constricted. So more constriction of the veins, then we're going to see greater blood pressure. If more veins are now relaxed, because they're, then we're going to see a decrease in blood pressure. Okay, so peripheral resistance has a big role in blood pressure. And then finally, we can control peripheral resistance not just by monitoring the through these reflexes, but local chemical control can also change or alter peripheral resistance. So and it can do that by relaxing precapillary sphincters. So if we have low oxygen and high CO2, and also a decrease in pH, so more acidic conditions, and these are all the kinds of conditions that we find in active tissues, that signals relaxation and dilation of precapillary sphincters, and as a result we see more blood flow into those tissues. So the more of these capillary networks that we open up, the lower the blood pressure will be. And some of the chemicals that are used to signal for this are nitric oxide, NO gas, that's dissolved in the blood, and chemicals referred to as bradykinins, because and the work of both nitrous oxide and these bradykinins is to cause vasodilation, which then results in a decreased blood pressure. On the other hand, epinephrine, norepinephrine, those are very similar chemicals. And then chemicals called angiotensin, and it's specifically angiotensin 2, and another capillary or tunica interna made chemical called endothelin. These all cause vasoconstriction, which will increase blood pressure. So that kind of sympathetic stimulation that we get from epinephrine and norepinephrine is going to cause a rapid increase in blood pressure. All right. Oops. Don't know how that happened. Wait, that was it. We're done. That's how that happened. Okay, so we have looked at blood pressure and the control of blood pressure, and we've seen that blood pressure is produced, or we see blood pressure in the arterial system as a result of cardiac output, as a result of the blood volume, as a result of peripheral resistance, and as a result of blood viscosity. Those are all factors that influence blood pressure. And we've also discussed how the body can actively change the pressure of the blood by looking at this Frank-Starling law of the heart and the reflexes that are available through the baroreceptors and their stimulation or inhibition of the cardioaccelerator and cardioinhibitor reflexes, and how peripheral resistance can be altered by changing the precapillary sphincter activity and by either dilating or constricting blood vessels. So there we go.